homework on my whiteboard last night. It was amazing.
You discovered the power of what?
I have discovered the power of whiteboards.
They're amazing.
Oh, gosh.
All right, let's talk about heaps.
Heaps of heaps?
Heaps of heaps.
Heaps of stacks.
I watched a video of when does a heap stop being a heap?
When you start ordering it, right? Is that it?
Well, heap is just like many things.
Isn't a heap like a literal thing where it's literally just a pile of stuff?
So it's a sloppy tree.
Oh, okay.
It's got some structure to it, but not as much as a binary search tree.
So it's like that crabapple tree out in the backyard.
Yeah, yeah. So maybe a lazy tree or a tree made by someone lazy. What?
A hedge.
A hedge.
Oh my god.
So there's two kinds of heaps: max heaps and min heaps. So max heap. So the largest value is at the root. A min heap, the smallest value is at the root. And for now, let's just stick with max heaps. Okay, just because it doesn't really make any difference. Actually, you know what? Let's do min heaps because we did max heaps last period. So this will balance it out. So let's just focus on min heaps. So we're going to talk about structures where the smallest element is at the root of the tree. But here's the only requirement for things to be a heap. Each node must satisfy the heap property. So for a min heap, this means each node is less than its children. So the data value stored in a node is less than the value of the children. Could be less than or equal to. I'm not going to put duplicates in, but you can. So here's a picture of a heap. So there's a heap. So each node, I violated my heap property so many times. There we go. All right, so each node is smaller than the value of its immediate children. And it's because of this that the smallest value of all is going to be at the root. If you work through it kind of inducting on the number of levels in the tree, you can convince yourself that this cannot be bigger than anything else in the tree, because if it is, somewhere that heap property is being violated. Okay, so the smallest value will be at the root. The other thing about a heap is it's always filled in this order. Right, we're going to completely have nodes on this level before we get anything on the next level down. And on the lowest level, everything to the left will be populated, everything to the right of some spot will be empty. So the tree is always nice and full. We can't have a bunch of stuff coming down one side and some stuff missing from the other side. Okay, if we wanted to add another number to this heap, it's going to have to be the left child of 30. And the next number after that will be the right child of 30. The next number will be the left of 7, and then the right of 7. And only then, if we add another number, will it be a left child of 21.
So there's no difference greater than 1 between numbers like that?
Correct, right. Every leaf will have either a depth D or D minus 1.
What if we want to add 29 next?
So if we wanted to add a 29, it would come right down here. But then we'd violate the heap property. But this is still where it starts. Okay, so how do we add things to a heap? So adding to a heap. So add to lowest level rightmost position. Or if there's no space left on the lowest level, start a new level. So let's add a 29, it's going to go right here. Okay, now we're going to do something called upheaping. Which means check the parent. If the heap property is violated, swap the parent with the smallest child. Alright, so we added a 29. Now we check its parent and see if the heap property is satisfied, and as you've noticed, it's not. So we're going to swap that 30 with the smallest of its two children. Well, it only has one child, 29. So we're going to do this. This will be 29. This will be 30. And then we're going to check that node's parent. So we're going to check 29's parent. That's 3. Does that satisfy the heap property? Yes, it does. We're done. Okay, if heap property is violated, swap with smallest. Else we're done. Okay, let's add a 1. So the 1's going to go right here. And we're going to check the parent for the heap property. The heap property is violated because 29 is not smaller than 1. So swap 29 with the smaller child. And now check 1's parent, that's 3. That also violates the heap property. So swap 3 with a smaller child, which in this case is again 1. So this becomes a 3. And now check 1's parent, 2. Heap property is violated here also, so swap 2 with the smaller child. This becomes a 1, this becomes a 2. We don't have a parent to check, so we're done. And this is a heap. So let's do that a few more times. So here's a 1, 10, 20, 21, 41, 40, 122, 128. There's a 2, 7, 3, 30, it's 29. All right, what should we add? Someone give me your favorite number.
413.
18? All right. And we check the parent, 7. That still satisfies the heap property. We're done. All right, what was your number?
Well, I suppose it wouldn't be much use to point anything out since it's greater than 7.
Well, we'll put it in there anyway because that'll get us down to a new level. So we put in 413. Heap property of 7 is still satisfied. We're good. Okay, you said 6? Mm-hmm. Okay, so there's nothing else we can do on this level, so we have to start a new level. There's our 6. Check the parents for the heap property. 21 violates the heap, so swap 21 with the smaller child. This becomes a 6. This becomes a 21. Check the parent. 20 violates the heap property, so swap that with the smaller child. This becomes a 6. This becomes a 20. Check the 10 for the heap property. It's still violated, so swap with the smaller child. This becomes a 6. This becomes our 10. Check the parent 1 for the heap property. That's smaller than its children. We're done. So we can keep inserting into the heap by adding to the rightmost position on the lower level, or the leftmost open position on the lower level, if you like, and then upheaping. So upheap means check your parent. If the heap property is violated, swap with the smaller child, and then move up to that node's parent. Keep going till either the heap property is satisfied or you've run out of nodes.
So this doesn't seem too much like it sorts.
Doesn't sort at all,
Okay.
right? And it's horrible for searching. If you want to search for a 3, there's no rhyme or reason to where that 3 is. Right, or if you want to search for, well, for anything. Right, if you're searching for 128, there's no reason why you would start off looking at the left subtree. Right? So it's not good for searching. But what it's really good for is pulling off your data in sorted order. So with a min heap, we can ask for the smallest number, and it's always just the root. So here's our 1, 6, 2, 3, 7, 30, 29, 18, 4, 13. We're about to delete. I should have made a smaller heap. All right, so we want the smallest number. Well, that's a 1. So it's always at the root. So that's a 1. And then we want to remove the 1 from the heap. So we're going to get rid of that. What are we going to put in its place? So 1, remove the root. 2,
Smallest child.
replace with the last number in the heap. In this case, it's that one. So last number means lowest level, rightmost number. Okay, because remember, we always want our heap to be as full as possible. So if we removed any other number except this one, we'd be violating that. So this number goes up into the root. And then we do what's called down heap. It's a dual to up heaping. We look at this, we see if the heap property is satisfied. If it's not, swap with the smaller child, and then down heap from here. Swap with the smaller child, down heap from here, heap property is satisfied, we're done. And we've got a heap again. And guess what, if we want the smallest number again, it's whatever's at the root now. That's a 2. Remove that, take the last node, which is 413, put that in the root, and then down heap. So 413, swap with the 6. 413, swap with the 10. And 413, swap with 20. And we've got a heap. So these are duals to each other. To insert, we put something at that last position, and then we upheap. To remove the root, we take the thing from the last position, plop it in the root, and then down heap. Okay, so you want to do these on your own. You want to get out some paper with some friends and make some heaps and add and remove from them. Okay, and you're going to see this on the test. So be familiar with this before then. Don't try to learn it during the exam. So removal, take the root out, replace it with the last thing in the tree, and then down heap. Check the heap property. If it's violated, swap with the smallest. Insertion, insert in the last place, and then up heap. Check the parent. If it violates the heap, swap with the smallest, move up to that node's parent, and keep going. And all of this flips around for a max heap. You still up heap and down heap in the same ways, but the process of down heaping for a max heap is to make sure, well, it's the heap property that changes. For a max heap, the heap property is each node should be bigger than its children. So when you're down heaping, compare the node to its children. If it's not bigger than its children, swap with the largest child, and then move down and keep going. And for up heap, you just go up.
Real quick.
Yeah.
It all happened so fast.
Yeah.
So you took the 21 from the bottom left and replaced the top node with it, and then you looked for the smallest child and replaced it, and looked for the smallest child again and replaced it. Kept doing that? Yeah. Okay.
So let's take a smaller heap so we can.
I guess when you down heap, if you have it really big, you end up having to play with a bunch of nodes to kind of like shuffle it into place.
So let's see, min heap.
I guess down heaping is Is that generally more complex than upheaping?
They should be pretty much the same. So there's a more reasonable sized heap. So removal, right? Take out the root, replace it with the last entry, which is 12, and then down heap. So 12 is bigger than its children, so swap 12 with the smallest child, and then down heap from here. 12 is bigger than its children, so swap with the smallest child, and there's your heap. And then if you want to add something like 1, right, put it right here and upheap. 10 violates the heap property. I messed up. I didn't have a heap to start. There we go. All right, 10 violates the heap property, so swap with the smaller child, and then check this node's parent. 4 violates the heap property, so swap with the smaller child, and there's your heap. So when you insert or remove, you're either starting from a leaf and upheaping, possibly as far as the root, or you're starting from the root and downheaping, possibly all the way to a leaf. Now if you have n pieces of data, what's the height of your tree? Nominally speaking.
Log n.
It's nominally log n. And the number of steps that you have to go through to upheap or downheap is basically bounded by the number of levels in the tree, the height. So this insert or remove is an order log n operation. So pretty darn efficient, right? Trying to find the smallest number if you have a min heap, and then adjust the heap. Finding the smallest is an order 1, but then you have to adjust it to keep it heaped. That's a log n. And same with adding things to it. So here's the next question. Suppose you want to build a heap. You have n pieces of data. They're just kind of random numbers, and you want to build them into a min heap. How could you do that?
Sort of like a reverse bubble sort with the smallest, or I mean, obviously whichever min, max, whichever you're looking for.
Mm-hmm.
Do it one time, so you get the biggest or smallest on the top, and then take the rest of your data and just set the biggest or smallest to the root, and then dump everything in after that.
So just keep inserting, right?
Yeah.
Yeah. And you don't even need to find the largest or smallest to begin with. You can start with an empty heap and use this log n insertion to insert your first number, and then use this insertion to insert your second number, and do that for all n numbers. And that will end up being n log n operations. So it doesn't really sort your data per se, other than moving the smallest number to the root, but it puts it in a structure that lets you then pull off the data in sorted order with log n operations. So effectively it's an n log n sort. But it turns out we can build a heap more efficiently than that. And this is one of my favorite things about a heap. You can take a set of random data and you can do what's called heapifying. So here's how we heapify data, how we turn data into a heap. So spit out some numbers. Keep them 1 or 2 digits though.
7.
27. 57. 42. 77. 38. 3. 11. 1. 20. 0.
84?
19.
19, cool. All right, there's a bunch of data. And it is absolutely not a heap, although it started off, I was a little scared. It's definitely not a heap, right? 77 violates the heap property, 42 violates it, 17 violates it, and so on. All right, we're still thinking min heap. It turns out if you take your data and you just build a tree in the order that I just did, start filling in each level left to right, when you get to the end, go down to a new level. So you get this heap-like shape, right? And you end however much data you have, right? That lower level may not be full. The process of turning this into a heap is very efficient. So here's how this works. So heapifying data. One, start with the last number in your tree-like structure, so that's going to be a 19. If heap property is violated, then down heap from that point. So let's do this. 19. Does that satisfy the heap property? Well, yes, because it has no children. So in that vacuous if false then true kind of way, it's not bigger than any of its children. So this already satisfies the heap property. So does 84, 0, 20. In fact, everything on this level is fine. None of those violate the heap property. So we really need to come up to this second from the bottom level, and we look at this 9 and say, does that violate the heap property? Well, yes, it does. So we're going to down heap, which means swap it. No, that's a good value. That's smaller than both its children. All right, so nothing to do for the 9. 77 violates the heap property because that's not smaller than both children. So swap with the smaller child. So this becomes a 0, this becomes a 77. And then we would repeat with the 77. Well, 77 has no children, heap property satisfied, we're done. Okay, go over to the 42. That violates the property, so swap with the 1. This becomes a 42, and we're done. 17 violates the heap property. 3 is smaller, so swap with the 3, and we're done. And keep moving up through all the nodes until we get to the root. So 13 violates the property, so swap it with the 0. This becomes a 13, and then compare that to its children. That's fine. 27 violates the property, so swap it with the 1. So here's a 1, here's 27, and then compare 27 to its children. Violates the heap property. Swap it with the 11. There's our 27, and we're done. And that brings us to the root. So that violates the heap property. Swap with the smaller child. So this is a 0. This is a 7. This is 7 versus 30 or 9. That satisfies the heap property. So we are finished. Sorry, that's, I don't know if that's a 13 or 0. That's a 13. 7 versus 13 or 9. That satisfies the heap property. We're done. So we have 1, 7, 3, 38, 17, 11, 27, 42, and 7 is 13, 20, 77, and over here is 9, and 84, and 19. Unless we messed up, that should be a heap now. So each node is smaller than its children, and we're good to go with removing minimum elements. Okay, how much work do we have to do this heapify?
Worst case.
Worst case.
You have to down heap on everything you check.
If we have to down heap on everything that we check, that's going to be the worst case. And down heap, remember, is order log n, and we have n nodes. So at first cut, that feels like n log n again. But it's actually not. Because here's the cool thing about heapifying. Everything on our lower level already satisfies the heap property. That's half our data. Okay, if this is nice and full, half our data is on this lowest level. So if we have n pieces of data, half of that data we don't have to do anything with. A quarter of the remaining data is sitting on this second level from the bottom, and to down heap is going to take at most one operation. We're going to swap with a leaf node, and then we're going to be done down heaping. So 75% of our data, 3/4, we either do no work or we do a single operation. And 7/8 of our data, we do either no work or a single operation or 2 operations. And it's actually only 1/8 of our data that's going to require 2 operations. A quarter will require 1, a half will require none. And this worst case where we have to do n operations to down heap, there's only one piece of data out of all our data where that might happen, and that's the root. And where we have to do log n minus 1 operations, there's only 2 pieces of data where we might have to do that. So if you actually add this up, you end up with this 1 plus 1/2 plus 1/4 plus 1/8 kind of behavior, and this ends up being order n. And there's all kinds of really confusing derivations of that online, but that's basically the idea. Is at the higher levels where you have to do more work, there's significantly fewer nodes. And so it's not really log n added together n times. It's log n added together once, plus log n minus 1 added together twice, plus log n minus 2 added 4 times, and so on. And this is order n. So n pieces of data, you can turn it into a heap in order n operations, and then you can extract the smallest one in log n per piece of data. So heaps are pretty efficient if your data is such that you're just trying to pull it out in a fixed order. So typical example, priority queue in a job scheduler. So you want to store jobs in the structure, and you want to know which job has the highest priority. That's the job I'm going to run next. So you'd build a max heap, and you store your priorities in there, and then it's very efficient to pull out your highest priority job. All right, questions or comments so far? So here's the coolest thing about heaps. They're tree-like, but you can implement them without doing tree-like things. So here's a picture of a heap. I don't know why I drew that. Hopefully I can find the reason. Okay, I have a reason. We're going to store this data in an array. And we have this inherent ordering, right? When you're putting things into a heap, your first thing is going to go at the root, your second thing will go in B and then C, and your fourth thing would come down to a new level and you'd fill in D, E, F, G, and then you go to another level, H, I, J, K, and so on. So there's this inherent ordering. And we're going to store these nodes in an array in that same order. But the trick that makes this work, we're not going to use index 0. We're going to start with index 1. And we're going to store our elements as follows. So to store 15 pieces of data, we'll use an array of 16 elements. We skip the first element, and we just store sequentially. Now, what kinds of things do we need to do when we're heapifying, when we're up heaping, when we're down heaping? we need to find a node's parent and we need to find a node's children, right? So here's the trick. If we want to find node i's parent, where I is the index in this array, it's just I divided by 2, taken as an integer. And if we want to find the children of I, it's 2I and 2I plus 1. So for example, node E, suppose we want to find its 2 children so we can see if the heap property is satisfied. If E is stored at index 5, its children should be stored at index 10 and 11. That's J and K, that's the 2 children of E. And if you're upheaping and you want to find E's parent, E has index 5, 5 divided by 2 is 2, that's the index of its parent B. So we can store these in an array and we can move up and down the heap just by doing this simple index arithmetic. And that's actually pretty fun to code after you've been doing mallocs and pointers for a few weeks. It's nice to play with arrays. So we might want something like heap size equals 15. That'll tell us the index of the last thing, or the number of nodes in our heap. And you can make a function called parent and a function called child1, child2, or whatever. And now we can code these algorithms without too much pain. So let's do a removal. So how do we remove? Well, smallest is whatever's at the root, element 1 in our heap array. So we're going to remember that and return it eventually. And now we can say something like heap element 1 equals heap element heap size. So if heap size is 15, we take element 15, that's the last element here, and we copy it into position 1. That moves element O to the root. And we want to decrement heap size, so we can actually do that right here. So do a post decrement. So now heap size is 14, and O is sitting up here at the root. And now we can say something like down heap, starting at element 1. And then return smallest. And how do we insert? Well, we want to add our new element to whatever the next position is in our heap array. So we could say something like heap, and in this case it'll be a pre-increment on heap size equals n, and then upheap from heap size. Does that seem plausible? So the whole point here is that we want to do things like add something to the rightmost position on the lowest level or start a new level if the lowest level is already full. But all we got to do is increment heap size and store at that index in the array. And that's guaranteed to be the correct spot to insert. If we want to remove the last element, we just take the element indexed by heap size and then decrement heap size. And if our tree looks like this, if our heap looks like this, it'll give us an O. If our heap looked like this, it would give us the K. And when we decrement heap size, it effectively removes that from the heap and makes the heap one element smaller. So these relatively straightforward array operations take care of what we would do in a binary search tree with mallocing a new node and setting up pointers to it and things like that. So what about these heap operations? I'm gonna have to leave like 5 minutes early today, by the way. So you get 5 minutes to go outside. Let's look at down heap. So, well, if I is bigger than heap size, then we don't have to do anything. Otherwise, if heap I is less than heap of child 1 of I, and if it's less than heap of child 2 of I, then we're done. Otherwise, swap with the smallest. These should be brackets. So if heap child 1 of I is less than heap child 2 of I, then swap heap of I with heap of child 1 of I, and down heap child 1 of I. Else, same thing with child 2. So to down heap from, say, element 0, compare it to child 1. So I have two child functions. Child 1 is 2i, child 2 is 2i plus 1. Right, so compare it with its two children, and if it's not less than both of those, see which one of these is smallest. If child 1 is smaller, then swap element I with element corresponding to that child, and then down heap from this position. Otherwise, swap with child 2 and then down heap from child 2. And I wrote this recursively because that's the sense in which we've been doing this. To down heap from this point, we make an adjustment and then go down to the child that we moved and down heap from there. But we don't need to recurse, and we probably wouldn't recurse. Right? When you have recursion and the recursive call is the last thing you're doing, you can substitute it with a loop. So instead of down heaping from child 1i, we could just change I to be child 1's index and go back up to the top. And we could throw that all in a while loop while high is less than or equal to heap size. And along the way, if we find that the heap property is satisfied, then we just return. So down heaping is just a loop. and up heaping is exactly the same. It's just backwards or upside down maybe. So heaps are fun to code. I might have you code a heap in 223. I'm going to need to do like 20 assignments in 223. I got all these programs I want you to write. I might have you do a heap assignment. Just because it's fun. It's like very simple operations to get this really powerful behavior out. It's just putting them together in the right way. So down heaping, up heaping, pretty straightforward loops. So my question now is, does that give you what you need to do the homework? Let's take a look. Do you know which quizzes are heaps? 6?
Yes.
All right, let's take the quiz. Which of the following are true of heaps? Okay, you can answer that. In fact, these are some of the questions people have asked. Which of these is true of a max heap when inserting into a max heap? When implementing a heap in an array, that's this stuff. Which of the following is true? To remove the largest value stored in a max heap. Okay, I think you can do all of those. Is it just that one quiz?
Mm-hmm. Yeah, some of it was trees, I think.
Yeah.
Oh, okay. Cool.
So someone emailed you and they're like, just, randomly, random thought.
Random
Which one of
question.
these do you think would be exactly true for
While
heaps?
inserting into a max heap. Yeah. Cool.
You're like, man, they think a lot like me.
Yeah.
You think a lot like a Canvas quiz.
Yeah, right. All right, cool. So questions at heaps.
What are some of the main uses for heaps?
Mostly when you're storing data that you want to retrieve in a fixed order, either increasing or decreasing order. So the only example you ever find online is like a priority queue, but anything like that will work as an example.
Doesn't Valgrind say it uses a heap when it gives you?
There's a heap, which is the pool of memory from which malloc pulls data, and that apparently has nothing to do with with max heaps and min heaps like this. I don't know what the crossover is in the terminology. I've never dug into that. But you could use something like this to organize memory. You could organize memory by chunks of size, maybe. But I don't know if that would make sense. All right. Well, yes. No, we're done with ODPs. Good job. So I will write up some kind of a study guide by Wednesday and post that on Canvas. And Wednesday, I'd like to leave open just for like questions. And if there's no questions, we can just go through sort of everything, just kind of rehash the whole quarter. But much better if you bring questions or things you want clarification on.
SLP's tomorrow?
SLP is tomorrow, 3 o'clock. Digital Lounge, get here early if you want like prime locations to stand around. Your posters will be there. There will be a sign-in sheet, so sign in your name next to your name to let me know that you're there. There'll be yellow extra credit sheets, and looking forward to seeing what people have been doing. All right, so I will see you tomorrow.
My grade is fine, and I think it really takes away from somebody.
How much is the extra credit?